Thank you so much. And yes, welcome everyone. Welcome to this wonderful and strange lecture, Giant Bananas Spinning in Space. It's a beginner's guide to gravitational waves. Um, I'm sure all of you are wondering what on earth this is going to be about. I promise there is some real science to this. But just a quick introduction to myself. So I'm Deepali Lodhia. Call me Dee, it's much easier. I work at the UK Space Agency, and I'm also a committee member of the space group at the Institute of Physics. So as you can probably tell, I'm a real space nerd. So my background is in astrophysics. My PhD was in gravitational wave detection, which I did at the University of Birmingham. And that's what my lecture is going to be based on. So let me go on. Right, so gravitational waves. Everyone's been talking about them. They're quite a hot topic. They have been for a little while now. But what are they really? So everyone keeps talking about these gravitational waves. What does it mean? What do all these words mean? Well, I'll tell you what it isn't, okay? It's not gravity. So gravity is basically a force, an attractive force between two bodies, okay? So take yourself, for example, being on Earth. You're attracting the Earth and the Earth is attracting you, okay? So there's this attractive force between the two of you, and actually only one of you is winning because the Earth is so much bigger. So it ends up holding you, pulling you down towards its center there. Okay, so that's gravity. Okay, that's to do with the gravitational field. Gravitational waves, completely different. If you try to Google what is a gravitational wave, you might come up with something like this: ripples in space-time caused by an asymmetric accelerating body. And then you might see some sort of picture or video showing two bodies moving around, and you see all these waves swirling around. But what does that mean? Those words can be very, very confusing. So over the next few slides, what I'm going to do is I'm going to break that down, and we're going to work out what these gravitational waves actually are. So first of all, what's an asymmetric body? Well, here's a very smooth spherical ball that is symmetrical. Okay, so it's smooth on all sides. So no matter which way you hold it, it's completely smooth, looks the same in either direction. Okay, so that is symmetrical. Asymmetrical means something which isn't symmetrical, such as an asteroid. Okay, but also planets. As soon as you have any sort of imperfections on the surface of the planet, might be craters, might be a mountain, okay, you have an asymmetric body there. Something else which is asymmetric is a binary system. So you might have two stars orbiting around each other, or you might have a star and a planet, or a planet and a moon orbiting around each other. So as a system, it's an asymmetric body as a whole. Now, what do we mean by space-time? Well, let's take our three-dimensional world that we live in. Okay, so we have three axes there. We've got X, which is basically your left and right. You've got Y, that's your up and down. And then your Z, which is forwards and backwards. Okay, so we all live and think in a three-dimensional world. Okay, perfect. Now, let's add another dimension to that. Let's add time. Okay, so now we've got 4 dimensions. Our 3D world plus time, and then we're going to stick that onto a 2D sheet, which looks a bit like this. Okay, so you have to sort of try and imagine this, because as humans, we can't think in more than 3 dimensions. Okay, so we have to start playing around with how we represent things. So here's our space-time sheet, okay, 3D space plus time, and it's represented by this 2-dimensional sheet. Okay, it's a stretchy fabric. That's what I want you to imagine. And those grid lines on there, we like drawing those grid lines because then when we put anything heavy on it and the material stretches, we can actually see how it's stretching and how that fabric starts to bend. Okay, and then we can start to think about the curvature of space-time. So we take our stretchy space-time sheet and we put something heavy into the middle there. So you can see that heavy red ball there. And instantly you can see that it bends your stretchy fabric. And then the other thing that you can do is that curvature of space-time, that cleverly describes how other bodies will move around that large body. So you can see right there with a red heavy ball, there's another marble that's rolling around all the way around it. How does that happen? Well, let me show you this video here. So there's a metal ball there in the middle of a stretchy sheet. That's our space-time fabric there. And then if you throw another marble into it, and you can get it to go around and around, it ends up orbiting around your metal ball there. Now that blue marble, the small blue marble that's going round and round, it thinks it's traveling in a straight line. What it doesn't realize is that that metal ball has warped space-time, affecting the way bodies move, okay? Now, something that I want to explain about heavy objects sitting on this stretchy sheet, your space-time fabric. If you have something that's quite heavy, okay, so large mass, we say, something like the sun is very, very big, lots of mass. And if we were to put that on top of a stretchy sheet, obviously it would stretch. But then if we took something heavier, let's say a neutron star, it would stretch down a bit more, it'd go a bit deeper into that fabric there. Now, I wonder if any of you can think of anything that's even heavy. What's probably the most dense, heaviest object in the universe? Hopefully, most of you have guessed black holes. So we put that onto our stretchy sheet, and it bends the sheet so much, it creates this really, really deep well. If any sort of marble or any object even approaches the edge, it will fall straight in and it's not coming back out. Okay, no matter how fast it's moving, it just can't get back out. And the same applies for photons, for light. Okay, as soon as it comes into the boundary of that black hole and it falls into the well, it's not coming out. And that's why black holes look black. Okay, so we can't get any information out of them because there's no light being reflected back out towards us to give us any information. Okay, so the next words that we want to look at, an accelerating body. What's an accelerating body? Well, you might think, you know, traveling really fast in a car or a train or a plane, or maybe on top of a rocket. I don't recommend sitting on top of a rocket, but you can imagine when you accelerate, okay, you're not just traveling at the same constant speed, okay, you're getting faster and faster and faster. And sometimes you feel that when you're in a plane and you take off, or you're in a car and then the driver suddenly accelerates. So you would be an accelerating body. Another way you can accelerate, again, I don't recommend doing this, but Wile E. Coyote has kindly demonstrated for us. If you were to jump off a cliff and fall down, gravity, there's that force again, is going to pull you down, okay? So gravity is an accelerative force, okay? You get faster and faster and faster. Again, don't try this at home. Now, another form of acceleration that you might not have thought about is spinning. When you spin an object, you're accelerating it. Now, that seems a little bit strange because you think, well, if it's just spinning at a constant speed, surely that's not accelerating. Well, actually, this is the beauty of maths and science, because of the way that speed and velocity and acceleration work. The ball is, if you were to stick a dot on a basketball and then spin it, that dot is constantly changing direction all the time. And because of that, it means it's accelerating. And then if we take that idea, again, if we have a spinning, a binary system, two bodies spinning around each other, that is also accelerating. Okay, so those are some different definitions there of what an accelerating body might be. All right, so we're just going to go back to our stretchy space-time fabric and look at some spinning objects. So here's our 2D space-time well created by a very, very heavy object. Okay, so we just pop that heavy red ball into the middle there. Now, you can see that it's created a nice well at the bottom. If we were to then spin that ball, that red ball, the shape of the well, that's not going to change. It's just going to stay the same shape. Remember, this red ball, it's not asymmetric. It's perfectly smooth on all sides. Okay, so if you were to lower yourself down and just watch what's happening at the edge of the fabric, okay, you'd see that the well stays the same, the edges of the fabric, they don't really move up and down, everything just stays constant. You wouldn't even be able to tell that the ball was spinning around. Right, now, ripples in space-time. So how do you cause these ripples? Well, you need something that's asymmetric. So I hope you guys have your bananas ready. So this is where the real science kicks in. Right, you need to imagine, really try and be as imaginative as you can, okay? Your banana is a gigantic banana, and it's up in space, and it's really, really heavy, and it's on that stretchy sheet, okay? And it's lying flat on its side. Okay, so that's what you need to imagine. Really, really heavy banana. Okay, great. So what happens now is, you see how the sheet slopes. It's not quite even on both sides anymore, okay? Because the center of mass is all off, the banana is a funny shape. So you can see it slopes sort of in a shallow angle on one side, and then slopes quite steeply on the other side. And then we get that banana to spin around, and we start spinning it faster and faster and faster. What actually happens is those slopes on the edges, so one's quite steep there, the other one's a bit shallow, and as that banana is spinning around, it starts to move and move and move, and then you start to see fluctuations on the edge of your fabric. Okay, so it starts to move up and down, and they all spread out like ripples in a pond. And those are your gravitational waves. That's what you always see depicted in videos, okay? So all those waves that you see coming out, like here in the pond, it's those fluctuations, okay? The movement going up and down of something which is not symmetric, and it's accelerating, and it's causing the edge of your space-time fabric to move up and down really, really quickly. Okay, so I told you there was some science behind the banana. Right, so we've worked out what gravitational waves are, but whose bright idea was this? It was this guy. Of course it was this guy. So this is Einstein, Albert Einstein. He actually predicted the existence of gravitational waves in his general theory of relativity over 100 years ago in 1916. Obviously, we all know he was a very clever guy. Of course, he's going to come up with something like this. But he probably never imagined that we would ever be able to directly detect them, have the instruments that are sensitive enough. So yeah, he was only able to prove it using pure maths. And all that time, it was believed that these waves do exist, but there was never really any way that we could directly prove it until recently. But let's just come back to the waves again. So what do they look like to us? Forget the space-time fabric. What about in real life, in our 3 dimensions? What would happen if a gravitational wave were to just, pass through us? What would happen to the objects around us? Right, I want you to imagine that you're standing in a room and you've got these free-floating particles, okay? Don't ask me how, they're just floating there, okay? And they're in a ring, okay? So you've got all these particles there in a ring. And then a gravitational wave passes through, okay? So imagine it's passing through your screen right now. Just like that. Now, the effect that a gravitational wave would have in our 3D world is it distorts space-time, okay? So it's changing the distances between large free objects. And this is how it looks. This is what would happen if a gravitational wave were to pass through your screen, okay? And then all of these particles that are just floating there, it would stretch in one direction and then contract in the other. Okay, so stretching and squeezing and alternating. And in 3D, it actually looks quite cool. So this is a very nice simulation that was created to show what happens if you had loads of these rings, one behind the other. Now, something to remember is gravitational waves, they travel at the speed of light, but they are different to electromagnetic waves, okay, or light, photons. And this is because of the way that gravitational waves, they hardly interact with matter, and they do weaken over distance, but differently to electromagnetic waves, okay, so less so. And that gives it some very unique properties, which we'll come on to later on. Okay, great. So we've worked out what these gravitational waves are, what they're doing, how they move. Brilliant. Let's start measuring them. Okay, let's start detecting them. Well, if they're stretching and squeezing along two axes, then maybe you can just use an L-shaped ruler. That would make sense at first, right? But remember, gravitational waves, they affect actually everything, okay? They make everything stretch and squeeze. So that means that your ruler would also stretch and squeeze, so you actually can't measure anything. So that's a big no. What we can do is use something that has unusual properties, which is light. Okay, so remember, gravitational waves and light are very, very different. But because of the properties of light, we can actually use that as a ruler for gravitational waves. It sounds very strange, but it works. So here we go. Here's our L-shaped ruler with a little bit more added to it. Now, what you can see is on the left-hand side, you have a laser and it shoots along towards the right. In the middle, there's something called a beam splitter. So that's a special mirror and it lets 50% of the light through. Okay, so 50% of that laser beam would go all the way through, all the way to the right-hand side. But then 50% of the light would be reflected. So you can see half of that laser beam then goes up. And so you've got your L-shaped detector there, okay? Now, your laser beams will hit some mirrors at the end, then come back again, join up at the beam splitter, and then come out at the bottom there, and that's where your detector is, and you can see what the light is doing. And what you're hoping to see is one arm, okay, so your L-shaped detector there, so you've got two arms. One arm will stretch while the other one squeezes, and vice versa. Now, just thinking about what the detector sees, I'm just going to go over some of the science behind interference. So some of you might already know this, but just very quickly, where you have light traveling along your two arms, okay, and then they come back again. When you add them back again, so those are your two waves in that picture in the top left-hand corner, if the two peaks align, then that gives you a much higher peak, okay, that's constructive interference. Or if you've got an upside down peak, in other words, a trough, if you have two troughs and you add them together, you get a much deeper trough. When you get a really high peak or a really low trough, that will give you a signal, okay? There will be light shining on the detector. But if you've got a peak and then a trough and you add them together, well, that just cancels out. And then that leaves you with a flat line. And that's what you can see on the right-hand side there. That's destructive interference, okay? So the two waves cancel each other out. And so your detector would see no light, okay? So it would switch between light and no light, light and no light. I'm just going to show you in this image here in the bottom left-hand corner. So we're holding one arm still, okay? So one of the waves is still there on the top. And then the second one is slowly moving along it. So that's just depicting, you know, a change in the arm length. And then you can see when the troughs line up, that thick blue line shows what the detector is seeing at the end. And it goes really, really high. And then it cancels out because you've got a trough and a wave, for example. And then they come back again. So you might have two troughs. Okay, so it's constantly moving through, going on, off, as you get peak cancellation, trough cancellation. And so this is what ends up happening with your detector. as your two arms stretch and squeeze, alternating, you can just see there at the bottom, you can see that blinking light, okay? So it's coming on and then goes off when it cancels out, on, off when it cancels out. And these are the signals that we're looking for, okay? And that tells us that there is a change in length of the arms. It's actually really, really clever science. Okay, so now that we've sorted that out, brilliant. We know what our detector should look like. It should basically just be an L shape. Okay, great. Let's go and build some detectors. So I'm going to show you some pictures of what we call advanced LIGO. So that's the Laser Interferometer Gravitational Wave Observatory. Okay, there are two of these detectors in the USA. Here's one in Washington State. So that's a Hanford detector. And the other one is in Livingston, Louisiana, also in the US. Now you can see that those arms are quite long. They are really, really long. Actually, each arm is 4 kilometers long. Probably weren't expecting that. If you're struggling to understand how long 4 kilometers is, if you take a football pitch and take the longest side, and then you take 36 of those pitches, you line them all up along the long side, that's how long 4 kilometers is. So it's pretty long. Okay, so that's where they are. One on one side of the USA, the other on the other side. So actually it's quite good that they're situated like this. And just to show you which way that they're pointing, we don't want them pointing the same way. So these aren't to scale, the red and the yellow aren't to scale, but it's just to show you that they're pointing in different directions, because obviously we want to try and cover as much of the sky as possible. Okay, so if we're covering different directions, it's even better. And they're 3,000 kilometers apart, right? So that's actually quite a good distance to be able to capture gravitational waves. Okay, covers a much larger area of sky. Just want to show you some pictures inside Advanced LIGO. I wish I could show you loads and loads, but I've just picked out a few here. Remember the picture I showed you of, what a detector looks like, just a really simplified version with the beam splitter in the middle? Well, actually, this is what it ends up being, okay? A bit more complicated. There's a lot more stuff inside, a lot more mirrors, lots of cleaning and stabilizing of the laser beam, lots of different detectors. So yeah, there's a lot more to it than people realize. So this shows, you can see the Y arm and the X arm there, just sort of in the top right hand corner. Obviously we can't fit 4 kilometer long arms on this diagram, so we've shrunk them down there. But the next picture I'm about to show you contains the laser. Well, basically everything on the left-hand side. So the laser, the input mode cleaner, power recycling mirror, and the beam splitter. So here we go. That's all of that, all the way from the laser beam, the main laser beam, all the way up to the beam splitter. It's quite big, very big area there. And here are the mirrors. The mirrors are quite special, and they're very close to my heart, because this is what I worked on for my PhD, or at least part of it. These mirrors are huge, okay, and they sit there as pendulums. All right, so they're almost swinging pendulums, and they're controlled very, very carefully, because obviously you don't want to attach them to the ground. If you start having earthquakes, the detector is going to pick it up. If you've got cars traveling past, the detector will pick it up. The detector is so sensitive that it can even pick up vibrations from planes going overhead. Okay, so it is a super, super sensitive detector, and it can pick up everything. So these mirrors, okay, they need to be what we call seismically isolated. So just dampening down all the other external vibrational noise there. These mirrors, they're quite big. Okay, so if you have a ruler, for example, they're just slightly bigger than your ruler. So they're about 35 to 40 centimeters in diameter, okay, from one side to the other. They're quite heavy. Okay, so you can see, especially that mirror there at the bottom on the left-hand side, it's got sort of a pinky reddy colour to it. That's just the reflective coating on there. But each of those mirrors, they're 40 kilograms each. To give you an idea of how heavy that is, it's the average weight of a baby calf, or for any adults out there, it's the weight of a standard dishwasher. So there you go. So yeah, very heavy mirrors. So you can imagine what sort of technology goes into suspending them on these delicate glass silica fiber wires. The sensors that I worked on for my PhD, you can't quite see it in those pictures, but if I bring up another one here, so just above the pinkish mirror there, near the top, you can see those 4 deep holes. So the sensors sit inside there and they basically help to detect any external vibrations and then feed it back and then hold the mirror still. Okay, so they sense and they actuate. And here's a quick preview of what happens inside the main control room. Now, these laser beams, they're traveling through these huge vacuum tubes. Okay, so you can't have people walking around inside. So it's all locked off, but that's why we have lots and lots of detectors down there. And that's what you can see in these TV screens. Okay, so you can actually see some of the laser beams, those white blobs, they might sort of look like a planet or a moon on a whole bunch of those screens there. That's actually the laser beam. Okay, to the human eye, these beams are invisible, but obviously we've got the technology to be able to see them. All right, brilliant. So we've figured out a way to detect these gravitational waves. Where are they actually coming from? There are specific sources that we want the strongest sources possible to be able to detect these gravitational waves, because by the time they reach us, they are much weaker. So here we go. So this video, you can see 2 neutron stars and they're spiraling around each other, and then they get faster and faster, and then finally they come together, they create a black hole, they merge into one, and they release a whole load of energy in the form of gravitational waves. Here's another video as well to show you what happens. So here we've got 2 black holes. There's our stretchy fabric of space-time, and now you understand what those ripples mean and how they're caused. But yeah, they spiral in, they get closer and closer, and then just release this massive amount of energy, and then everything calms down. So actually the signal that we're looking for, well, it looks a bit like this. So you can see in the bottom there, you've got your 2 spiraling black holes, and they get a little bit closer. So in that blue line at the bottom there, you can see this gravitational wave signal, let's say, okay, it starts to fluctuate more and more, and then the black holes come together even closer, and then we start to see this blue wave. And then during the merger phase, that's when the most energy is released. So that's the orange part of the wave you can see there. Okay, so all those waves, they bunch together. That means that they're high in frequency, and they've elongated. That means that amplitude has increased, giving off lots of energy, and then finally it rings down. Okay, and then you end up with usually a black hole there. So that orange part, it's sometimes referred to as a chirp. Okay, because technically, if we could hear a gravitational wave, it would sound like an increasing frequency and then a chirp, and then it would die down. Now that chirp, it doesn't last for very long, and we'll come on to that later. And then finally, gravitational waves, they were detected for the first time ever. It was a surprise. So advanced LIGO was it was an upgraded version of the previous detector, LIGO, okay? So it went from first generation, and then everything was upgraded and made more sensitive and better and more powerful, and then we ended up with the second generation called advanced LIGO. And when advanced LIGO was first switched on, the story is that they hadn't even built up to full sensitivity of that new detector. They'd only just started warming it up, and then suddenly it started to detect these signals, so it was completely unexpected. And in fact, I remember during my PhD, we weren't even sure if second generation detectors would be able to detect any signals. We'd have to wait until the third or even fourth generation. So here's what the signal looks like. So you can see in the top there, in orange, that's what the Hanford detector detected. And then the Livingston detector, that's, you can see that in blue there. And then when you put them together, they match quite well. They're not perfectly matched because remember, they are facing in slightly different directions. Okay, so for one detector, the gravitational wave might be coming in one way, but then for the other one, because it's slightly on the, further along the globe, it might be coming at a slightly different angle. Okay, so the data was thoroughly analysed. They realised it couldn't have been anything else. And yeah, everything matched. It was a hit, and it was a really, really big deal. So the actual detection happened on the 14th of September 2015. A long time was spent on confirming this and also confirming where it came from, how it happened, all of that stuff. The data analysis team, they came in and did, worked their magic, worked it all out, and it was officially announced on 11th of February in 2016. And I remember this because I was called in the night before. I was invited to appear on BBC Breakfast to talk about this. So there I am, first thing on the 11th of February, early in the morning, trying to explain what gravitational waves were. It was really exciting. So this first event, okay, this first detection, it's been named GW150914. It's to do with the date convention, naming convention. So where did it come from? They found that this particular signal came from two spiraling black holes. Okay, so two black holes spiraling around each other, and it's 1.4 billion light years away. That's really, really far away. That means that the light from there to here, it takes 1.4 billion years for light to travel. Okay, and that's exactly how long it took for the gravitational wave signal to travel. Really, really far away. Now, the actual signal, that chirp signal, if you remember, I was talking about the in the orange part of the graph, it lasted for 0.2 seconds. It's quite quick. It was over very, very quickly. And where was it located from our perspective on Earth? It was actually in the southern hemisphere, so near the Large Magellanic Cloud. So just at the bottom there, you can see some colourful lines. So in that yellow area, okay, just near the bottom there, that's where it's believed to have come from. So that's our view of the sky there. Now, here's some very cool things about that event. So these two black holes, okay, we also managed to work out their masses because we have some very clever scientists. One black hole, it had 35 times the mass of our sun. The other black hole had 30 times the mass of our sun, very roughly. And then when they merged together to form the final black hole, that resulted in a mass of about 62 times our sun. Now, if you look at the numbers, the maths doesn't quite add up. And that's because, well, we're missing three solar masses, three masses of our sun. Where did that go? It actually radiated away in the form of gravitational waves. 3 times the mass of our sun. That's a lot of energy. It's absolutely remarkable. And as you can imagine, that led to a Nobel Prize. So it went to these three guys here, Barish, Thorne and Weiss. So yeah, Nobel Prize in Physics, because this was absolutely groundbreaking. It's opened up a new window to the universe. Okay, it's opened up a new branch of astronomy called gravitational wave astronomy. Now, since then, we've detected over 200 gravitational waves. I'm still counting. But well, what's the big deal? You might be sitting there wondering, okay, well, this is all fine, but how does it affect me? Like, how's it going to change our lives? Well, first of all, in the world of science, it's going to change a lot of things, especially in the way that we can observe the universe and find out more about what things are made of and how they move. So gravitational waves, they can travel through the universe more easily than light. Okay, so they're not affected by matter quite as much. That means that they can travel through, they'll still stretch and squeeze objects, but they can still travel through them. And that means ultimately we might be able to finally look inside a black hole and work out what is going on inside. We can't do that at the moment. We can't use light, okay, to look inside. We certainly can't send humans to a black hole or even machines or spacecraft or anything. It'll just be ripped apart. But with gravitational waves, once we learn how to manipulate them, we might be able to see inside black holes. We might also be able to work out what happened at the point of the Big Bang. Okay, so we're trying to go back really far in time and work out how the universe started. We've got most of it worked out, but at the point of the Big Bang, at the actual 0 point, we just don't know what happened, what set it off. We cannot go back to that particular point. Gravitational waves might help us to. So there's actually quite a lot in science that they can help us with. But thinking about all the technology, the transferable technology as well. Okay, so we have pushed the boundaries of technology, of science, really. And now we can apply all that newly found knowledge to things like flaw detection in carbon aircraft with the way that we can control the lasers. Okay, it can be applied to ultra-stable optical clocks. It can even be applied to laser welding and medical applications. Okay, so the way that we can stabilize these lasers and make them even more powerful and really clean them out and make them pure. But there's loads of other things. There's the mirror coatings, okay, the ultra smooth surfaces. These mirrors are some of the smoothest man-made surfaces that we have at the moment. Okay, we can use the technology for laser defense, super sensitive sensors, new bonding techniques we've developed, new vacuum cable clamps. There are so many different things that we can apply this technology to. So it's not just about, thinking about the future and the long term. Actually, we can apply all this amazing technology to our lives at the moment. Okay, so we've got detectors all over the world, or at least we're planning to. I've pointed out the ones in the US. You can see them on the left-hand side. We've got the 2 LIGO detectors, Hanford and Livingston. There's also one in Virgo, also L-shaped. It's 3 kilometers long. And there's a smaller one, 600 meters long, in Germany. There's one that's under construction in Japan, which is called Kagra. That's going to be 3 kilometers long, and one planned in India. So that's going to be part of LIGO. And all these detectors, they're all going to work together and try to collect as much data as possible and spot even more gravitational waves. And they'll be able to capture more parts of the sky, more areas of the sky. You might see there at the top, there's something called LISA there with the 3 red balls in the top right-hand corner. Come on to that in a second. There are plans for something called an Einstein telescope. That's going to be 10 kilometers long. That's going to be in a triangular shape. And then there are ideas for a cosmic explorer. So that's going to be L-shaped, but 40 kilometers long. Right. I won't spend too long on this slide, but just to show you that you can use different detectors to look for gravitational waves from different sources. Okay, so on the bottom there, on the right-hand side, you can see the ground-based interferometers. Then next to it, you've got the space-based ones. You can then use radio telescopes as pulsar timing arrays. Okay, so we've got lots of different ways of doing this now. And this one is very exciting. So it's a space-based gravitational detector, which is just amazing. It's called LISA. It stands for Laser Interferometer Space Antenna. And yeah, it's just going to be floating around in space. It's in a triangular form, so it's going to be 3 spacecraft, and then they're going to shoot out lasers to form a triangle. Each arm, each side of the triangle will be 2.5 million kilometers long. And when a gravitational wave passes through, this is how it will stretch and squeeze. And it's planned for 2035. And just to show you LISA's orbit, so it's going to follow the Earth in its orbit around the sun. So it's going to try and capture even more gravitational wave signals from around the universe. Okay, so this is my last slide now, and I just want to finish off trying to explain how amazing our technology is and what it's actually detecting. So how much are we detecting? I did say that gravitational waves, they do get weaker. So here's an atom. Atoms are very, very small, as you all know. You can see the electrons whizzing around the nucleus there. Inside the nucleus, you've got the red balls, which are the protons, and then the blue balls, the neutrons. Let's concentrate on the proton. So let's zoom into the proton there. This is very small. And what I want you to do is split that diameter. So from one side to the other, split that distance into 10,000 parts. And you're left with something really, really tiny. Okay. Now remember this. So remember our arms, our detector arms? We are looking for a change in length between them. And that change in length is equivalent to exactly what I just said with splitting the diameter of the proton into 10,000 parts. It's 1/10,000th the diameter of a proton, which is that much. And there you can see there are lots of zeros there. That's how small the change in the length of those 4-kilometer arms we're talking about. And that's why these detectors are so sensitive. And the fact that we've managed to achieve this, it is a huge accomplishment. Okay, folks, so that brings me to the end. Thank you so much. I hope you enjoyed that. I hope that made sense. And yeah, next time you're talking to anyone about gravitational waves, just explain to them about the spinning bananas. Thank you.